everyone. Hello, everyone. Welcome to our point distribution webinar. Our today's speaker is Jordi Marzo from University of Barcelona, and the title of his talk, Quadrature Rules, Risk Energies, Discrepancies, and Elliptic Polynomials. And please do not forget that after the talk, we have some social time or like virtual coffee break. So please, Jordi.
Okay, so well, thank you all for coming, and thank you for the opportunity to talk. And well, as you can see in the title, there are a lot of things, and I will start with the first. So this quadrature rules, and well, at any moment if you want to ask something, just unmute yourself and go ahead. And okay, so well, most of the things, or yeah, I will say most of the things I'm going to talk about are true in a more general context, maybe, I don't know, Riemannian manifolds, some of them, or maybe a more restricted setting, but I will focus, basically, I will talk all the time about the sphere, okay? And at the end, I'm even going to move to the S2, okay? But, well, I can give you a reference if you want for some of the results in general, but well, as I said, my main focus is going to be the sphere. And on this sphere, ST, yeah, the first problem is this quadrature rules, trying to find quadrature rules. And by this, I mean the following. So we want to find an approximation of the integral for functions in some class, just using basically the evaluation of these functions in some fixed points, well, maybe with some weights, depending also on only on these points. And we would like to have some error estimates. Okay, so we want to have some way to approximate this integral, and well, I will basically present just a way to do it, and my goal here is well, to try to talk about an interesting open problem, I think, and well, it's going to be a motivation for what's coming next. Okay. So it's not a survey about quadrature rules. So it's just something about quadrature rules. And okay, but first I will define the space, and the space is, or the spaces are going to be the spaces of polynomials. PL is going to be, well, these are, well, if you want spaces in D+1 variables of degree at most L, and you can consider the restriction to the sphere, and this is going to be PL. And in here, I will take this scalar product. And well, it can be shown that the dimension of this space, I will call this HL, so I will drop this D. HL is more or less is of order L to the power D. Okay? For example, in S2, this is exactly equal to, so HL is L+1 squared. But okay, to define our quadrature rule, I'm going to use something called Fekete points. Okay, and these points are defined in the following way. So you can choose you choose any orthonormal basis in Pn, and then you can consider this function, the determinant of this matrix. Okay, so this Q, I are polynomials and orthonormal basis, fixed pieces, and the function is a function on the points. Okay, so you have here xjl, these are HL points on the sphere, and these points are called Fekete, or also extremal fundamental systems, if the value of this absolute value of the determinant is maximal. Okay. And well, these points are very good for interpolation. And are going to see now basically why, but first I will show you some picture. So these are 129 Fekete points from one of these Bommersley lists, and I download the points, and well, this of course is just one side of the sphere S2, but as you can see here, well, you can imagine. So this is almost a triangular lattice. Okay, so it's a very nice family of points on the sphere. Very difficult to compute, but very nice. And once you have these Fekete points, well, you can do this in general, but for these Fekete points, I'm going to define the corresponding Lagrange polynomials. So here I have the definition. So I have my points, these are Fekete points, and I define the following. So here I have this determinant. So this is the first, so this is the same quantity, and here, well, without these absolute values, okay? So I have the determinant of this, of a basis in the points. And here on top, well, I have the same thing, but I changed this I column. Okay? So this is to define the polynomial L sub I. And I replace this xi else here by just an x. Okay? So this is just replacing this xi L by x. And this is defining, so this is a polynomial in PL, because these Qs are bases in PL. And these polynomials satisfy a very nice property, well, a couple of them, and these are the ones I want to stress. So the first is that they actually interpolate, so well, yes, the Lagrange polynomials. So by definition, they satisfy this. So if you just take any of these xj's, well, of course, then you repeat a column, and the polynomial is 0 as soon as I is different than j. Okay? And when they are equal, then you have the same thing on top and here on the denominator, and then it's 1. So this is the Kronecker delta at these points. And so you have these very nice polynomials, and for a fixed value I, so this is 1 in xi, and it's 0 in the other points. Okay, and moreover, so it's just by the definition of Fekete points, these polynomials are bounded by 1. Okay, it's very easy to see also, because if you take absolute values here, well, we know this is the maximum value, and this is just a collection of points, and where you replace xi by x. So at most you will get the maximum. Okay, so this is a smaller in absolute value than this absolute value here. So this is bounded by 1. Okay. Okay, so you have these very nice polynomials, and now I'm going to define the quadrature rule. And for this, the observation is that, well, if you take any polynomial in PL, then you can write Q in this form, because, well, of course, you can see on the left, on the right, these two polynomials coincide in these xj's, and they have the same degree, so these are equal. Okay, so this Q can be written in this way, and therefore you want to integrate. All you have to do is just take an integral here, and well, by linearity, it will just go all the way up to integrating these L's. Okay, so the integral of Q is the sum of these integrals in these L's. And these are the integration weights. Okay, so this is, well, I just call these integrals of these Lagrange polynomials. We call this WJL. Okay. Let me see. Okay. And now to give some intuition about these integration weights, I will recall something about the Piketty points, kind of an old result we proved with Kim Ortega. These Piketty points are asymptotically uniformly distributed. Okay, so this means that if you, so you can take that as the definition if you want. So for every function, continuous function in SD, if you consider this average of this continuous function, well, now you have here 1 over the number of points. This converge when L goes to infinity to the integral of f. Well, just because later I will talk about discrepancies, there's also this equivalent condition. If you define the spherical cap discrepancy, or the L infinity spherical cap discrepancy, so this object here, this of infinity of this set of points, well, so this is the definition, okay, of this spherical cap discrepancy, and this definition is just the supremum when C runs through all the spherical caps on the sphere of this difference, and this difference is basically just measuring the difference between the counting measure. We are just counting here the number of points this set in C, all divided by the total number of points, minus the surface measure. Okay, the normalized surface measure. So it's just measuring this discrepancy between these two measures. And in terms of this object, this the spherical cap discrepancy, you have the following. So I don't know if this was a question. Or, well, I will continue. So then, yeah, the point is that these points are asymptotically uniformly distributed. So this is, if this is the definition, this is equivalent to this fact. So the spherical cap discrepancy goes to 0 when L goes to infinity. Okay, so these are, and then somehow you can imagine that a way to measure the well distribution of a family of points is to control somehow the velocity of this. Okay, but well, the main point is this: these points are uniformly asymptotically uniformly distributed, and therefore the intuition comes now. Okay, so the thing is, we have this Piketty points xj, so we have a fixed polynomial, and in PL if you want, and then if I consider this sum, so now I have this sum now with HL. Okay, so I have this, so the same weight for all these xj's. Okay, just by this uniform equidistribution, this converges to the integral of Q. But we know that if Q is a polynomial of the right degree, then this is equal to this quadrature expression. Okay, so the evaluation of the polynomial in the points times these weights. Okay, and therefore you can see here that more or less the point is that, well, you have the same quantity except in these weights. So the intuition is that these WJs are somehow like 1 over HL. Yeah, or this is a way to justify it somehow. Of course, this is not the proof, but I mean, it's kind of, they should be kind of going towards this 1 over the number of points. But and well, indeed, if you consider some, well, if you check the numerics, well, when it's available, but here, for example, I have a picture of well, this misprint, so it's 4 times the weights. Okay, so I consider these 256 Piketty points, well, again from Bomersley Web, and I compute the weights. Okay, these WJs, and I just plot the weights here. Okay, and as you can see, if I compute 1 over HL, well, this should be 4 for pi times this, because well, this was not normalized. But this was 0.049, so this is something kind of like here. And indeed, more or less, the weights are kind of close to this value, okay? Because the scale is well, it's kind of small. Okay, so these are, of course, they are not equal to HL. Okay, this is not possible to find equal weights, but they are kind of close. Okay, and well, this is just numerical evidence of this, but the open problem I want to mention first is well, there's well, in fact, there was conjecture by Sloan and Bommersley that these weights for Fickety points are positive. Okay, so this is kind of the least you can ask for a quadrature formula, to have positive weights, because if not, somehow this will become unstable from a numerical point of view. Okay, but so here we are saying much more than just positive. Okay, but this is just numerics. But well, this is of course just a conjecture, but it will be, well, based on numerics and numerical evidence, well, up to this degree, okay, up to 191. So that's a lot of points. But well, it's kind of well, it's kind of a shame that we are really far from this. Okay, what it's known is it's really it's dramatically far from this. Okay. The only result in this well, about this problem is this is a paper by Reimer from '93, proving that the weights are positive in P2. Okay, so this is L equals 2. Okay, so this is actually a paper, and some things that have to be computed there to prove it. So it's a very difficult problem, but I mean, it's a kind of well, kind of annoying that that it's so hard to say something about even the positivity of these weights. Okay. But well, as I said, so apart from this, from defining these quadrature formulas, we would like to have something about the error. And well, it's kind of natural to think that, well, this integration error is somehow it's going to depend on the regularity of the function. And therefore it's natural to try to consider a chain of spaces with increasing, or with where you can measure this regularity. Okay, and this is why I'm going to introduce now Sobolev spaces. Well, just the definition. So I'm going to define these Sobolev spaces on the sphere, and for this you can do the following. So if you consider HL the space of spherical harmonics of degree L, or if you want the eigenvectors of this eigenvalue, so these are these HLs, then well, you can decompose L2 in this orthogonal sum and have some Fourier expansion. Okay, so this Fourier series of F is just well, scalar product against this basis. Okay, this is just an orthonormal basis in HL. Okay, and then I'm going to define the Sobolev space H super S. This is the set of functions in L2 satisfying this bound. Okay, so this thing here is bounded. And well, I'm going to take this as well, the square root of the norm. Okay, the norm is the square root of this guy here. And well, it's very easy to see then that you have this increasing So the biggest space is H0, which is L2. And then you have these nested, these included spaces, and with more and more regular functions, okay? Well, in fact, HS is embedded in CK if S is strictly greater than K plus D halves, okay? So if you want continuous functions, you have to take S bigger than D halves. Okay? But okay, so we have here this chain of spaces, and in terms of this, I will apply a recent result by Luan Wang, answering question by Veroshenik. So this is just a particular case what I'm going to mention, but it's related with this Fekete points. So using that these Fekete points actually form something called a Marcinkiewicz-Sigmund family, you can get the following. So in terms of, so now we are going to try to say something about the error in this integration, okay? Well, there's a small technical detail here, so we cannot deal with HL. I have to enlarge a little bit this space, and going to take epsilon. And I take this x1 to xn, it's a set of n, if you want, Fekete points, but now not for HL, not for PL, but for P, well, floor 1 plus epsilon L, okay? So it's slightly bigger than L. In any case, the interesting point here is that this is of the same order, okay, L to the power D. And if you compute the corresponding weights, so here I drop this L on top, okay, then you will have the following result. For any S within D half, so as soon as you have a continuous function, this the error where you compute the well, instead of the integral, you compute this sum with the weights, is bounded by this quantity n to the power minus S over D. Okay? And in fact, this is well, due to some what has been shown by Brohard and Hess in the case of the sphere thing, and well, you have also a paper by all these people, Vandolini, Charat, and the others for Riemannian manifolds. You have also lower bound of the same order. Okay, so basically this is saying that these points are very good in terms of error because this bound is as good as it can be. Okay. And but well, of course, the problem here, or one problem that you can imagine, is that these Fekete points are basically impossible to compute. And although these integration weights are well, you just have to are independent of the functions. So once you have this in a list or whatever, you can just use for any function. But in any case, it's basically impossible to compute these points and the weights. And well, given this second somehow intuition that this weight should be like 1 over n, then it's natural to try to think about what's happening in the case of equal weights. Okay? And now this is my next thing. So now I'm going to consider the same problem. So to somehow evaluate this this error, but now with equal weights. Okay, so somehow with Chebyshev quadratures. And well, here there's a lot of things have been done, not by me, but by many others. But I mean, the thing is that okay, so now I'm going to survey, or just to recall some of the things I'm going to need afterwards. Well, this error now, where well, the only thing changing here is that here for this Fekete I have these WJs, and I'm considering well the same quantity, but with weight 1 over n. Okay. Then when you consider this this object, okay, the supremum, when you run through all these functions in the Sobolev space, of bounded norm. Then this error, this is called this worst case error, given the set of points xn and the smoothness s. Okay. And well, as I said, so these previous results from here, we know that you have a lower bound, no matter the points xn, you have a lower bound of this order. Okay. And okay. And some other interesting things happen here because let me see if I have something. Okay. Then, okay, here, this is basically a definition. But yeah, no, I'm not going to talk about the definition. So let's see this. I have this this general, this universal lower bound, and then something that can be shown in order to somehow to measure this this regularity of the points is that if you have that some set of points is equivalent to this value. So if you have also the upper bound, okay, for some s, for some regularity s, and this is called, or this, or then you say that this xn is a quasi Monte Carlo design for hs. So if you have this for some s, then you have the same property for any intermediate s prime between s and d halves. Okay, so for all these other spaces, you have it for free. Okay. These are basically results from a paper by Brohar, Sav, Sloan, and Bomersley from 2014. Okay, and well, the nice thing here is that well, this is basically saying that okay, so you have all these things for free in between, but you have a point where you can kind of reach, and this is somehow saying how good are these points. Okay. And this larger s, the larger s, you can where you have this property. This is well, that paper is called the strength. Okay, this is the strength of these families of points xn's. Okay, so in terms of this object, more or less, well, of course, this the here have the same weight, but in terms of this, we saw that there was no restriction for S in this previous result, okay, for 50 points. So that this was true for all S, okay. But now we are going to see the things that change quite a lot now. And okay. The first thing I'm going to okay, so well, some examples of this strength. So that is the first is that, well, using some previous results, I think again from Brohart and Hess, and at least in the setting of the sphere, and using this the result by Bondarenko, Radchenko, and Vyazovska about optimal spherical designs. One can deduce that spherical T designs form a QMC design for all HS, for all S. So these have like infinite strength. But in some other cases, you have some restriction. For example, well, there's this nice relation between the worst case error and the energy. So this is true on the sphere basically because of the form of the reproducing kernel of the solvable space, but well, it's also shown in this paper. So these are basically all results from this paper. And once you have this, you can see using estimates of the Rees energy, kind of all results from Wagner, you can prove that this the energy minimizers, so this energy maximizers in this case, because I have a minus here, so I want to minimize this worst case error, I have to maximize this quantity here. So this exponent is positive. These energy maximizers form quasi-Monte Carlo design in this range. Okay, and in fact this is optimal. So the strength is B halves plus 1. Okay? Just because it's kind of close to this, I will recall that, well, using Stolarski's formula, you can see from here that the worst case error in this particular case, T plus 1/2, is exactly the L2 discrepancy. Okay, so before I talk about this L infinity discrepancy, where you measure the difference between this counting measure and the surface measure, and there I took a supremum in all these spherical caps. But instead of a supremum, you can imagine that you can take an integral. Okay? If you take the L2 average of this discrepancy, then you get this L2 discrepancy. Okay? And well, of course, the L2 discrepancy is bounded by the L infinity discrepancy. But well, just to give you an extra property of this worst case error. Okay, more things from this paper by Brochar and the others. They actually did some numerical studies, of course, in S2, trying to determine the strength of this of some known configurations. Okay, and quite surprisingly, I think well, in fact, they conjecture that these are the right values. Okay, so there's a conjecture. I think that nothing is known in this about this, but the conjecture is that, for example, for Fekete points. So before we saw that with this weight, this wj's given by these Lagrange polynomials, we can go up to infinity, okay, with the regularity. But if we have a fixed weight, then they conjecture that the strength is 3/2. Okay? And okay, some other just to show you that the conjectures are different. So for Coulomb energy minimizers, the conjecture was that the strength was 2. And for minimal logarithmic energy is 3. Okay? But well, I think that nothing is known for certain in this about these values. It would be very nice to know, I think. But and of course, well, as usual, when you cannot deal with deterministic points, is to try to do something randomly, and then you can somehow deal with let's say worst case error in expectation. Okay, so you can using basically this property. Okay, because as you can see here, you are going to be able to say something about the expected worst case error as soon as you can say something about the expected energy. Okay, so this is kind of the link. And using this, they were able to prove again that, for example, well, uniform and independent points are not as good. And this can be shown, for example, with this, because if you try to use uniform and independent points, these are not QMC for any S. Yeah, these are really far from being good points in terms of integration. Okay. Well, points which behave much better are these jittered sampling points. So if you consider area regular partition on the sphere and you take uniformly a point on each of these area regular small pieces of the sphere, then they actually prove that points are in average, they are quasi Monte Carlo for in this range, okay, for and not farther. Okay, but of course this is all in expectation. And well, just to mention something more, so all these are just basically results from this paper by Brohart, and the only extra thing mentioning here is that if you consider something called the spherical ensemble, so these are points which live on the sphere S2, and they come from this from the random matrix wall, and they are really kind of well distributed. But well, using previous estimates for the energies by Ali, Hashi, and Samani, it out proved that they have the same scope as this jitter sampling. So from, well, when b equals 2, there's one from 1 to 2. Okay. And kind of a different approach was used by Berman to show that you can have even some results about almost sure configurations. Okay? Almost surely, say something almost surely, okay? Because these are just basically just things about in expectation. But using the concentration results for the spherical ensemble, you can say something, well, you could say a bit more about how good are these points from the spherical ensemble in terms of integration. Okay, well, this is just to complete a little bit this picture. Okay, and then this is basically what I wanted to introduce about this worst case errors. So and now I will move to something. To the edges. Okay, so here I talked about this maximizing this sum here, because this power here is positive. So I'm going to talk about extremal energies in so now I'm just moving to S2. Okay, extremal energy. So so I can define, if I have a set of points, or n points on the sphere, and some parameter as I can define these Rees energies, so in terms of this Rees interaction between points. And well, there's also this logarithmic energy, somehow the derivative of 0 of this, if you want. So you have these Rees energies, and now if S is positive, then it makes sense to try to minimize this object here, and the configurations where you attain this minimum, they will have some minimal energy, okay, that I will denote by calligraphic E, okay. And when S is negative, of course, then, well, the point is that you have here this guy on top, and then you want to maximize, okay, this expression. So this is why I'm talking about extremal energy. So you want to minimize when S is positive and maximize when they are negative. And okay. Then in this, about these energies, something you can try to study is somehow the asymptotic expansion of this minimal energy. And well, some things are known for a lot of things about this and proofs and everything. You can check this recent book by Vodashov, Hartin, and Sav. But I'm going to mention basically this conjecture. Okay. So the conjecture is that so the conjecture is not by it's mine. So it's I think it was Brocher and Hardin Sav and Bomersley, I think, in the paper. But well, the point is that you have this the minimal energy is conjectured to behave like this. So you have this first term, and then you have a second term. So this value is negative, actually, in this power n to the 1 plus s over 2, okay? And then smaller order terms. What it's known, I think, is that this quantity here is bounded by, this minus this first term is bounded by some negative constant times this n to this power, and it's also bounded below by another negative constant times this value. Okay, but I think that by now we're still far from this conjecture. Okay? But this is the value that it's supposed to be the one. And well, in general, this is a very difficult problem, except, well, of course, when s equals -2, okay? Because if you consider this e -2, so this will be just this expression. So we want to, so this will be the energy of this set x, this vector x, if you want. And well, you can just write this, and then it's very easy to see that this is 2 times n squared minus 2 times this quantity. Okay? And this, of course, the center of mass. So, and this is minus something positive. So from here you can get that the minimal, and well, here we have negative s, so this is maximal. So the maximal energy in this case is going to be 2n squared. And this is going to happen precisely when your points have a 0 center of mass. Okay? So as soon as you have this property, then you will obtain this maximum. Okay. Okay, but as I said, so for so this is the conjecture, but the known results are well, in terms of some constants here. So I'm going to recall some of these results. Well, but just basically in this range, okay, for positive s between 0 and 2. Well, the first is well, it's not the first result about this, but the first result I'm going to mention is by Rachmanov, Saf, and Su. Well, again, using some area regular partition. This is not random, but I mean, they consider this partition and some points in there. They were able to prove that for any epsilon, this minimal energy is bounded by the right main term. Okay, so this is the right guy. And then you have some negative value, which is 1 over this. Okay? And the corresponding power, at least for big enough n. And okay, here we have sort of a gap, and then something different you can do is so, because, well, of course the problem is that this is very difficult to compute the energy, or to estimate, or even to have examples is very difficult. So again, a good strategy is to try to deal or to try to work with random points. And okay, but the main goal then, it will be to have a good random points, because if you consider, for example, just uniformly distributed independent random points on the sphere, these are not good enough to have something of this order here. Okay, so this is very easy to check. But if you consider something better, for example, I mentioned already this spherical ensemble. So in 2015, Ali Shahi and Samani used this spherical ensemble to compute the expected number, so the expected energy, risk energy of points given by this spherical ensemble. And the result is this. So you have the same main term, and then you have this other bound. Okay? So this is, we are going to see now a picture. This is better, okay, than this one. Okay. So I know I'm skipping a lot of things, but anyway, the point is, let's basically move to our last ingredient, which is elliptic polynomials. Okay, so now I'm going to try to say something about these things I've been mentioning in the case of zeros of elliptic polynomials. Okay, these elliptic polynomials, well, these are also known as SU2 or Koszalin-Schutz-Meyer polynomials. But here you have the definition. Okay, so the point is that you have points. So these are polynomials in C. Okay, so as you can see, so the square root of n choose j, and aj now is these are normal, independent, complex random variables. Okay, standard, normal, complex random variables. And so these are random objects. Okay, and therefore the zeros are also random objects. But they behave surprisingly well. Okay, so you have this picture I borrowed from this paper by Marzo and Jordi, and here you have the picture of this set J's, if you want, these zeros, okay, in the plane. But then when you move these to the sphere by the stereographic projection, you have very nice points on the sphere. Okay, so these are these projections. Okay, so you have these elliptic polynomials with these random zeros, and the points are somehow nicely distributed on the sphere. Okay, and the good thing is that somehow these points behave better than these other points from spherical ensemble in terms of energies, at least. Okay. And this was shown, for example, for the first time, I think, in this paper I mentioned already. So considering, so this probability distribution here can be somehow justified in a more abstract way, because this corresponds to consider some Hermitian structure in the space of homogeneous polynomials. And considering this kind of Riemannian connection, so Armentano, Bertrand, and Schutz were able to compute exactly the expected energy, well, logarithmic energy in this case. Okay, so you have this very nice closed expression just with 3 terms. And okay, but the difficult thing here was that this Riemannian kind of approach is difficult to extend to other Ries energies. Okay, but then, well, something different was done also in this setting by these other people. Okay, so they consider Zeldich and Zong, and afterwards Feng and Zeldich. They consider somehow this also this as a more, so these polynomials in a more general setting of holomorphic sections in Riemannian surfaces and, well, Riemann surfaces, and they were then able to compute the expected, well, or to estimate at least, to have some terms of the asymptotic expansion of the expected Ries energy. Okay, so these are again, these xn are again zeros of the elliptic polynomials, and I'm computing the expectation of the Ries energy. And, well, as you can see here, I have well, again, this first main term, and the result is basically this. Okay, so, well, as I said, so the result is much more general. But I mean, if you specify this to the sphere, you get this. So to the sphere S2. Okay, so you have some constant times this n to the 1 plus s halves. But here again, you have some drawbacks. Well, the first is that there's no explicit value for this CS. And well, kind of a surprising thing is they cannot recover this other result. Okay, so because they have to estimate some function there, and they were not able to cut this series here. Okay, so it's not it's a different approach, and kind of well, has a different strength somehow. Okay, but then But then the point was, okay, but we saw this connection between this worst case error and the energy, and we want to say something about this. Well, we need a bit more about the energies, okay? And this is my last thing, because I'm just going to present some results together with my. So these are is a joint work, or kind of in progress, with my PhD student, also from the University of Barcelona, Victor de la Torre. And well, it's not in the archive yet, but I hope this summer it's gonna help us to finish really soon. Okay. And the thing is now the following. So the point is that we saw these two different ways to study the zeros of these elliptic polynomials, but there's a somehow simpler approach, which is to consider these functions here as a Gaussian field, if you want. Okay, so if you want for each z, this is a Gaussian function of a well-known and studied class called Gaussian analytic function. Okay, so these are Gaussian analytic functions, and then there are formulas for the so-called joint intensities of the zero sets, Hammersley's formulas. And although they look a little bit intimidating, seeing that at some particular cases this has been computed, then well, it's reasonable to try to say something about these energies using this approach, okay? Because basically to compute the expected energy, all you need is to control this second intensity. Okay, and this is basically our result, okay? If you consider now points in S2, points which are zeros of these elliptic polynomials, so you have these points drawn randomly from these elliptic polynomials, then the expected S energy is given by, also the asymptotic expansion of this is in terms of this familiar first term. And then you have some constant times this term, and this is explicit expression in terms of gamma and zeta functions. And even you can compute the next term, this term with n to the power s halves, which is again in terms of this function. Okay, so now it's c times s minus 2. Okay, and you have terms of small o of this n to the power n s minus 2, s over 2. Okay? And okay, and well, we can also recover so it's not so difficult to recover this logarithmic case also from Armentano, Beltran, and Schub using this this approach of computing this joint intensities. Okay. Okay, and well, the good thing is that here we have this this explicit term, and in fact we even need this second. Okay, because well, just for comparison, as I said, so let's compare this these different values for the energy. So I have this. Oops, it was here. Yeah. I mentioned these upper bounds. So you have this first, this other by Ali Shahi and Samani, and you have these pictures here. Okay, so this is the first, Ali Hashim Tamani. This is the conjecture, and this is our constant. Okay, so as you can see, well, these are all the signs are changed to have something positive. But I mean, the point is that the first value by Rachmanov and the others was this green, well, kind of far from the conjecture one, this blue. So this second, Ali Hashim Tamani kept closer, and then our value is even closer. Okay, so this is C, our minus CS, so it's even closer to this. And well, the nice thing is that it also kind of recovers this vanishing dipole phenomena. Okay, you have that this CS is 0 when S equals -2. Okay, so well, of course, this is not the minimal value, so you have some extra things, but the constant term here is it vanishes. Okay, so you have some kind of extra drop in this energy, so they kind of behave better than other configurations that are not even getting close to this value. And then from this, you can get the results. So by using this this expected Reese energy, and you need here the whole range. So for S from -2 to -4, and I would like to stress that you also need this extra coefficient, so the one with n to the power s halves. Then you will get that the expected worst case error is of the right order, so it's a QMC configuration, these xn's, so the zeros of these elliptic polynomials, for s between 1 and 3. So okay, so they go, so they are kind of as good as minimal logarithmic points somehow. Okay, and not further. So okay, so basically this is all I wanted to say. So thank you for your attention.
Thank you very much. Nice talk. Let's send the speaker. And please, some questions, comments.
Actually, I have a, hi, Jordi, it's Norm Levenberg. Hi, good to see you. Very nice talk, thank you. I have maybe a stupid question. I mean, when you're dealing with elliptic polynomials or these Gaussian analytic functions, of course, these IID coefficients that are these standard complex normals are the natural assumption, but do people care, or would it be interesting to see if you can extend things in this probabilistic sense to more general coefficients that may be close to standard complex Gaussians?
Well, I know there are a lot of things about this, and I guess people care, for example, about if you have something close to big Gaussian, if this is not to have some universality or things like that. So it's yeah, I think that it's of course if you have something more general, is going to be more difficult because it's kind of the simplest kind of guide that you can imagine. But yeah, for sure, it's I mean, there's a lot of other questions. I don't know if about energy, but for sure about other things. I've seen things about, for example, this universality and how these properties are somehow linked to the distribution.
But not with respect to your energy questions. That hasn't been. That's not so interesting, or perhaps, or
not that I know. I don't know.
Okay, thank you.
Please, some other questions, comments.
Hi.
Hi.
Hi, Jordi, great talk. So I don't remember if the discrepancy is known or not for these roots of random polynomials. Is it?
For this elliptic?
I mean, the worst case error you plug in, you deduce the discrepancy from there too, right? Yeah,
well, you can use this to get something about the expected L2 discrepancy. Yeah. And for this, you will get a bound, I guess. But in general, so I mean, these are all results about, I guess. Yeah, about the expected L2 discrepancy, I think you can get something, but it will be difficult, I guess, to get something more, because.
So you can't get the L infinity discrepancy from that?
No, I don't think so, because because well, for example, this Berman, he was able to say something about the L-infinity discrepancy of this spherical ensemble, just proving somehow from scratch something about the concentration in this case. It's kind of a hard thing and very particular this spherical ensemble in particular is a determinant point process, and I think that this kind of plays a role in his case. But for elliptic polynomials, I don't know. I guess you will have to have something. Well, something is known. I guess, for example, these points are asymptotically uniformly distributed almost surely. This was proved by Seldich and Schiffman. But the result, I think, is not quantitative. It's just that they know that almost surely this converge. Yeah.
Just one small remark on that, on Carlos' question. So you can estimate the L-infinity discrepancy in terms of the L2 discrepancy, but the results you get are very, very weak. And I think as soon as you try to use one of those, say, analytic constructions of point, like minimizing something like these Fekete ideas or whatever, as soon as you try to transfer that to estimates for the L-infinity discrepancy, you get very, very weak bounds for the L-infinity discrepancy at first. And secondly, there's one result about I think some Reese energies that you definitely do not reach the optimal order for L-infinity discrepancy with these minimal energy constructions.
Great. Thank
you.
And please some other questions, comments, remarks. Okay. Actually, I have two questions, maybe stupid, but what if instead of arbitrary coefficients, you will take some fixed coefficients? Will it be easier to calculate the Reese energy, or it doesn't matter? To get like some exact estimations.
Oh, they're asking about the entering in the library. So it's, okay. So you were mentioning to change the coefficients somehow.
Yeah, if for example, instead of arbitrary coefficients, you will take some fixed coefficients. Will it be possible to calculate, to get more exact estimations for this energy, for example?
I don't know. Because you mean this square root of n choose j to change this?
Oh yeah, maybe you can give like more terms, like whatever, just if you.
Yeah. I don't know. Well, this model somehow is related with other things, and I guess people will expect that this is kind of the natural, so the one that you can actually deal with, and then I don't know if any other setting will be even more complicated, although this may look a bit artificial, maybe, no? But even so, simplifying these things, maybe it's not so. Maybe it's not going to simplify the last the computations, because it's not going to reflect some invariance and some nice properties that you have when you have the right coefficients.
Oh, okay. I just saw that it was
so
probably will be with some exact coefficients will be probably possible to write down some like exact estimation for them.
Oh, but you mean so instead of considering random?
Yeah, instead of random, to have some like fixed polynomial.
Well, I guess this. I don't know if anything is known about this. Well, of course, you have some random values. They somehow concentrate around the mean, and you have something close there. Maybe you can say something, but I don't know.
Okay. And just second question, is it possible to use a method which was used for faculty points to some other, to apply this method to some other points?
Which part exactly?
It was like in the first part of your talk for the worst case error of the estimations for faculty points. Is it possible to apply these methods for?
Oh, you mean this result by Lu and? Definitively. Yeah. It's a more general result. It says true for any. So as soon as you have what they call this Marcinkiewicz-Sigmund inequality.
Yeah, but I mean, like, instead of faculty point, if to consider some different points.
Yeah. Instead of this, you can. So as soon as you have points that satisfy some sampling properties, then you can apply the result, and it will be the same. Yeah.
Okay, thank you.
So these are just a particular case of points satisfying this property to be sampling points or optimal sampling points somehow.
Okay. Thank you. Please, some other questions, comments? Okay, if it's not the case, let's thank the speaker once again. Thank you very much. Very nice talk.
Thank you.
And this, please stay for